Hello, this is Reasonable Faith Adelaide, and tonight we're privileged to have back our director, Kevin Rogers, from his long holiday. And he's going to be speaking tonight on, is the universe a free lunch? And personally, the idea of free lunch appeals, so I'm hoping the answer is yes. But I've got a feeling it's probably got a little bit more to do with the question, did the universe magically create itself out of nothing? Anyway, I'll hand over to Kevin now and we can find out what it's about.
Thank you very much, Brian, and I'll just get straight into it. In A Universe from Nothing, the book written by Krauss, he claims that the universe is the ultimate free lunch. And the basis of the claim is as follows. Gravitational energy, which I've abbreviated to GE, is negative. The gravitational energy cancels out all other positive energy forms, such that the net energy of the universe is zero. Thus, the creation of the universe requires no energy input and is the ultimate free lunch. Krauss is a member of the New Atheists, and so as far as he's concerned, that means that there's no need for God. And in brackets, I put in apart from a cause, because it doesn't answer the issue of a cause. So we're talking about energy, and energy can come in various different forms. So we've got I'll move the participants. So we have pictures of various types of energy, but they're listed here on the left. So you can get kinetic energy, which is the energy of motion. Then you can have various types of potential energy, which includes gravitational energy, the elastic spring. So if you've got a spring, you can pull it or compress it. And also chemical energy is also a form of potential energy. You can also have thermal energy, which is heat, electrical energy, magnetic, nuclear, radiant energy, mechanical, or sound. And so they're shown in picture form on the right-hand side. But what is energy? Sometimes this is fairly hard to define. But energy is the ability to do work. And it's, in mechanical systems, for a constant force, work equals force times distance, or energy equals F times D, where F is force and D is distance. So that means is the more force you apply, the more energy is required, and if you push it a long distance, then more energy is required. So that is the assumption that F is constant. But in general, work equals energy, and we've got this expression, an integral. So it's the integral of force as a function of distance times distance, and from a starting point to an ending point. So this is what we call a definite integral. But what it basically means is it's the average force times the distance that you move it. And people who've done a science degree, maths degree, or engineering degree will be very familiar with the idea of integral. But if you actually did mathematics at school up to final year, you would have done a subject called calculus, and that would cover differentiation and integration. But a lot of the concepts associated with this, you don't have to get too upset about the mathematics, because a lot of it can be translated into common sense. The other thing about energy is the conservation of energy. So energy can be neither created nor destroyed, but it can be converted from one form into another. So when you pick up an object and you drop it, it emits a sound, and eventually that sound energy is converted into heat energy. So higher forms of energy can easily be used to do work. e.g. light, chemical, electrical. So electrical, you have an electricity supply, it drives motors, runs heaters and television sets and all this sort of thing. So electrical energy is very easy to use. And if you have petrol, put it in your car. That's a form of chemical energy. It goes into the motor and it's ignited, it generates explosions and it's converted into mechanical energy. Now, is energy positive or negative? Well, it depends on the type. So energy forms that are positive only are, say, a spring. So you can stretch it in one way and you have to put energy into it, or you can compress it. And either way, the energy is positive. And anything that has a square term in it can only be positive, because if you square any negative number, it becomes a positive number. So kinetic energy is half mv squared. So if you have an object like a ball, throw it, it has a mass and it has a velocity, and the kinetic energy is half mv squared. So it doesn't matter which direction you throw it, the energy is still going to be positive. Now, thermal energy, I haven't put the formula in here, but thermal energy is related to the temperature of an object. So the temperature, so the minimum temperature is minus 273 Kelvin, and so you can't go lower than that. So you can only go above it. So thermal energy, or heat, is always positive energy. Now, if you actually use an electricity supply to heat a radiator, the radiator is a resistor, and the power through that is I squared R, and the energy, you get, energy is power times time, so you can only get positive energy out of a radiator, you can't get negative energy out of it. And in electrical, you can also store energy in things like capacitors and inductors, and again, you get a square of the voltage, or a square of the current, and you get this half again. And so that can only be positive energy. So also, if you have a radiator, it emits heat and light. The amount of energy that it emits is proportional to the fourth power of temperature. So that can only be, because that's squared, so it's, that can only be positive. But there are other energy forms that can be positive or negative. And so gravitational energy is one of those things. Now the indefinite integrals here goes k minus g m1 m2 on r. So m1 and m2 are two masses, g is a gravitational constant, and r is the distance between the two masses. Now it's got a negative sign here, but it's got a k in front of it. That's an undefined constant, and that is extremely important. The reason why this is so is this expression is what you call the indefinite integral. So it's got a term which is related to, is the distance between the two objects, but it's the value now. But it doesn't tell you what it was before. And so, it's like this. How far is it to Adelaide? Depends on where you are. All right? So if you're at Table College, it might be, say, 6 k's. If you're from Modbury, as we are, it's probably around about 26 k's. So if you have an indefinite integral, you can't say what the integral is because you only have the destination, but you don't have the starting point. Does that make sense? And all right, then the next term, it's got the definite integral. So it includes the initial point, which is R1, and the destination, and the final radius, which is R2. So you've actually defined both the beginning and the end, and so you can work out the answer exactly. So in this expression, if you actually start with, say, a small distance between the objects, and you end up with a bigger one, this term here ends up being positive. So it's positive if R2 is bigger than R1, and it's negative if R2 is less than R1. Does that make sense? All right. Now here we have the electrostatic, which is the energy for two charged particles, and those charged particles can be different or they can be the same. So if the charges are both the same, or are the same, not both the same, then they repel each other. Like charges repel and unlike charges attract. So if you've got like charges, they repel each other, so you have to apply force to bring them together. And if they are unlike, you have to apply force to stretch them apart. You let them go, they'll come back together. And so that allows the energy to be either positive or negative. And one is positive when you compress, and the other is positive when you pull them apart. Now, tonight we're going to talk about, develop the argument about is gravitational energy positive or negative based on Newton's equations. And because as soon as you have multiple objects or greater than two objects, it gets really complicated. So all the discussion assumes you've just got two masses, all right? And all the arguments that are on the web that I've seen are based on Newton's equations. You could make it really more complicated and go for general relativity, which at the moment is beyond my capability. But the existing arguments are all based on Newton's equations, because Newton's equations are very close to the answers you get out of general relativity, unless you get into extreme conditions. Now those extreme conditions would apply to the origin of the universe. But when you actually look out into outer space and you see stars and galaxies, then Newton's equations are pretty close to what you get out of general relativity. So Newton's gravitational force equation is this. Force at a distance, particular distance between the two objects, is g m1 m2 divided by r squared. So because it's dividing by r squared, the force falls away rapidly as the objects go further apart. And the force between the objects is quite high when they're very close together. So you and I, we're standing on the surface of the Earth, and we experience quite a tangible force between us and the ground, don't we? Right, it should be pretty obvious. Now, gravitational energy, you can say energy, potential energy, equals the integral of force times distance. And so we can just whack Fr into the equation. So G, M1 and M2 are all constants. And so you can just pull that out of the integral, and you're left with the integral of 1 on r squared. And the answer to that then is this undefined constant minus G, M1, M2 on r. So the integral of r squared is minus 1 on r. And so this is where the negative sign comes in, and people jump up and down in excitement about that. But we also have this thing, this undefined constant in front. So K is an undefined constant. When you actually do the definite integral, so you now calculating it between a start and a finish. R1's the starting distance between the two objects, R2 is the final. And what you then get is, again, the GM1, M2 is a constant, and you get this answer here. 1 on R1 minus 1 on R2. So energy is required. So if R2 is bigger, so you move it apart, then energy is required to go from R1 to R2. That make sense? Somebody's nodding, clear as mud. So positive energy is required to push two masses apart. Now that sounds a bit complicated, doesn't it? But just consider the diagram to the right. We have an instance of where a rocket is being launched into space. And so its initial location is the surface of the Earth. And we have to actually have an extremely large burst of energy to get it up into space. So that's basically what this formula means. That if you want to actually push things apart, you need positive energy. You need positive energy to launch a rocket or an aeroplane or anything else. All right? So that's a common sense interpretation of what all that maths says. Yes, I already got that. Now, here's where ChatGPT comes in. And I'll just I'll try and have my pretty face in there at the same time. So I got in ChatGPT and asked, is gravitational energy negative? And here's what it says. In general relativity, gravitational energy can be defined in different ways, depending on the context and the definition used. However, in some contexts, gravitational energy can indeed be negative. One way to understand this is through the concept of gravitational potential energy. The gravitational potential energy of an object is the amount of work that must be done to move the object from its current position to infinity. And here's where the confusion arises. Where the gravitational force is effectively zero, by convention, and that's extremely important, by convention, the gravitational potential energy at infinity is defined as zero, which means that the potential energy of an object in a gravitational field is negative. All right? But it's got this by convention. All right? For example, if you lift a ball off the ground, you are doing work against the gravitational force, and the ball gains potential energy. The potential energy is positive because you're moving the ball away from the source of the gravitational field, which is the Earth. On the other hand, if you drop the ball, the potential energy decreases because the ball is moving closer to the Earth, which is the source of the gravitational field. At the instant the ball hits the ground, its potential energy is zero, and its kinetic energy is at a maximum. So, in other words, if I grab some of the table's equipment and drop it to the ground, it will speed up as it goes down, and so its potential energy is maximum here, and its kinetic energy is maximum when it hits the ground, which is a risk to table equipment. In the context of general relativity, the concept of gravitational energy becomes more complex, and there are different ways to define it. However, in some cases, the total energy of a system that includes gravitational energy can be negative. This arises because the gravitational force is always attractive, and it tends to bring objects closer together, which results in a decrease in potential energy. True. This decrease in potential energy is compensated by an increase in kinetic energy, which is the energy of motion, so that the total energy of the system remains constant. However, because the potential energy is negative, the total energy of the system can also be negative. But bear in mind, it is a convention. All right? So I've made some notes on this. This is like assuming that zero height is the top of Mount Everest. For a mass in a gravitational field, potential energy plus kinetic energy is constant. When one goes down, one goes up, the other goes down, like a seesaw. So that does not mean that one is positive and the other is negative. Because if you've got a seesaw, you can have both seats above the ground. So it doesn't mean that one is positive and the other is negative. So consider a seesaw. When one end goes up, the other end goes down, but both ends are usually above ground level. Right. Is this just a convention? Is the gravitational, sorry, here's another question to ChatGPT. Is the gravitational energy at infinite separation actually zero, or is this just a convention? According to the convention in physics, the gravitational potential energy at infinite separation is considered to be zero. All right? This is because gravitational potential energy is defined as the work that must be done to bring two masses from an infinite distance apart to a given separation. So it's a definition, all right? It's not necessarily an absolute fact. So as the separation between the two masses approaches infinity, the work required to move them further apart becomes negligible and can be considered zero. However, it's important to note that this convention is a simplification and does not account for all the complexities of the gravitational interaction. In reality, the gravitational potential energy between two masses never becomes exactly zero, even at infinite separation, due to the long-range nature of the gravitational force. Nevertheless, the convention of setting the gravitational potential energy at infinite separation to zero is a useful approximation that allows physicists to make simplified calculations and understand the behaviour of systems at large distances. So it's a convention used to make maths simple. So I asked a question, well, why shouldn't gravitational energy be measured relative to zero separation instead of infinite separation? So here's the answer I got. Gravitational energy is a potential energy associated with the gravitational force between two objects. The gravitational potential energy between two objects depends on their separation distance, as well as their masses and the gravitational constant. The gravitational potential energy is typically measured relative to a reference point or position, which is usually chosen as a point at which the gravitational force between the two objects is zero. This reference point is often taken to be infinity, where the gravitational force becomes negligible. So you're with me at the moment? All right. If we were to measure gravitational energy relative to zero separation, it would mean that we are measuring the gravitational potential energy of two objects when they are at the same point or position. If it's zero separation, they're coincident, aren't they? At zero separation, the gravitational force between the objects would be infinite because you're dividing by r in Newton's equations, which would result in an infinite amount of potential energy. Therefore, measuring gravitational energy relative to zero separation is not practical or meaningful, as it would result in an infinite value that cannot be physically realised. Instead, we measure gravitational potential energy relative to a reference point where the gravitational force between the objects is zero, such as at infinite separation, which provides a practical and meaningful measurement of the potential energy associated with the gravitational force. Okay, now test. What do you think of that? Eh? Yeah, no. What does that mean? What do you mean by that?
It's not really saying anything.
Sorry?
It's not really saying anything.
Yeah. Well, actually, I've got a note down here. If I can get the participants out of the way. There's me. Points 3 and 4 are false. Whoops. Where am I? I've lost my participants. Eh? All right. Points 3 and 4 are false. If I can get... I'll just see if I can say escape. Stop share. I'll just run it again. Sorry about that. Right. The Newtonian force equation is F equals G times M1 times M2 divided by R squared. So that's the force, not the energy. So force is, the units of force are newtons. The direction of the force is between the mass centres for M1 and M2. And G is a gravitational constant, which is a very small number. So you need very massive objects before you can actually feel it. So R is the distance between the centres of mass for objects 1 and 2. But what happens when they're coincidence? The separation is 0. So on the right-hand side, I've got a couple of gentlemen from Wales who are descending down a mine shaft. So they're going underground, okay? So according to their logic, as you become more coincident, the F becomes undefined or infinite when R is 0. What's the direction of the force? If you got to the centre of the Earth?
No direction.
No direction. Would the force be infinite? Why not? Why do you say that?
Looks like it should be 0.
You're correct. Why?
Because there's no impetus to move anywhere.
What causes the force? It's on the lift and the men. What causes the force on it? It's all the mass around it, isn't it? And it's surrounded by mass, all pulling in the opposite direction, in different directions. So what would the net force on the men be?
In the centre, 0.
That'd be 0. So actually, if you go down that mine shaft towards the centre of the Earth, what's happening to the force?
Decreasing.
Say?
Decreasing.
It's decreasing, not increasing, so it's not rising to infinity at all. So the force equation that we have up here at the top, with R squared in the bottom, is only valid if the masses do not overlap. Because if you've got a man on top of the Earth, and here's your Earth, so when you actually descend down the mine shaft, the masses are overlapping, aren't they? All right? Does that make sense? So, the force equation is only valid for point masses, or if the masses do not overlap. So how can masses overlap? We've kind of already discussed this. So I'd consider this thought experiment. Imagine you dug a hole through the centre of the Earth. Sorry, I don't know what. I'll just get back to that point again. All right, there we go. So imagine you dug a hole through the centre of the Earth. So we've got a big hole. Sorry, what's the matter? Anne? All right. You're right. Yeah, for some reason I'm getting this funny rectangle there. I need an IT expert. So imagine you dug a hole through the centre of the Earth. You lower a mass, a small mass, towards the centre of the Earth with a strong piece of string. Okay? A long, strong piece of string. According to Newton's force equation, the force between the masses would rise to infinity when M1 reaches the centre. Is this true? No, it's not true. In fact, it would drop to zero when it reaches the centre and the direction would not matter. Make sense? So here we've got a numerical example. So assume your mass is 1 kilogram. When the mass is below the Earth, the force on the mass is roughly proportional to the distance from the centre. And it would be exactly that if the Earth was homogeneous. It's not. So there'd be slight wiggles and deviations from it, but it's a good approximation. So when the mass is below the Earth, the force on the mass is roughly proportional to the distance from the centre as the gravitational force from distributed surrounding matter cancels out. And if you kind of pulled it back up, the force would continue to rise until it hit 9.8 newtons at the surface, because the gravitational constant at the surface of the Earth is 9.8 newtons per whatever. So, and then if you could actually launch your mass into space, it would then follow Newton's equations. So, when you launch a rocket or launch your 1 kilogram mass to throw it up into the air, then the force decreases rapidly with increasing distance because it's 1 on r squared. So if you went to 2r, the force would be a quarter of what it was on the surface of the Earth. So we've got a graph of it in a program. So the axis, horizontal axis, is distance from the centre. So it's diameter, well, it should be radius over the radius of the Earth. So when it hits 1, you're at the surface. And 2, you're twice as far away as the radius. So in this bit below the Earth, below the surface of the Earth, is linear, and then when it's above the surface of the Earth, it drops off at the rate of 1 on r squared. So when the mass is below the Earth, the force on the mass is roughly proportional to the distance from the centre, as gravitational force from distributed surrounding matter cancels out. And it reaches 9.8 newtons at the surface. Above the Earth, it follows Newton's equation, and the force decreases rapidly with increasing distance. So, force and energy. Gravitational energy is the integral of the force. So on this right-hand side, we've got the force again. So this is below the surface of the Earth, this is above the surface of the Earth. And integration is just the area underneath the curve. So here it's calculated. So this is the energy relative to the centre of the Earth. And so from there to there, the blue, that's actually following r plus r squared. And then above the Earth, it's rolling off, and it's minus 1 on r. So below ground level, the force is proportional to r, and the energy, gravitational energy, is proportional to r squared. Above ground level, force is proportional to 1 on r squared, And the energy is proportional to this K minus 1 R, the undefined constant. Or it's now defined. We can now actually work out what it is. All right. What happens for non-overlapping matter? If you've got two solid objects and they don't have a hole through them, so what if the spheres, or the two masses, cannot overlap? Well, the distance between the centres is always greater than 0. So R equals 0 does not occur. So there's no problem. Now, what does the advantage of ChatGPT? It trawls all the literature, and so it can kind of give you a summary of different opinions in the literature. So I asked it the question: is the universe a free lunch? The question of whether the universe is a free lunch is a philosophical and scientific question that has been debated for centuries. In one sense, the universe can be seen as a free lunch because it exists without any apparent cause or explanation. But it's not answering the gravity question. However, this view is not widely accepted in modern science and philosophy. I don't think it's got much to do with philosophy, I think it's science. According to the prevailing scientific theory, the universe began with the Big Bang, a singular event that marked the beginning of space and time. While scientists do not know what caused the Big Bang, they have a good understanding of how it happened and how the universe has evolved since then. Yeah, so they don't claim to know what caused the Big Bang, but they think it's a reasonable model of what happened after the beginning. So it just describes it after the event rather than before. Now, some people may have problems with the Big Bang theory, but that is the mainstream view. Moreover, the laws of physics and the principles of causality suggest that everything in the universe must have a cause, even if we do not fully understand it. So while the universe may be a mystery in some ways, it is not generally considered to be a free lunch. So in here, it's kind of talking about cross purposes. So it's not looking at the universe from the point of view of being a free lunch regarding energy, requiring zero energy. It's looking at causality rather than energy. But anyway, that's the answer I got out of ChatGPT. So in summary, the question of whether the universe is a free lunch is still open to interpretation, but the prevailing scientific view is that everything in the universe has a cause, even if we do not fully understand it. But that answers talking about a different topic, really. Lawrence Krauss wrote a book called A Universe from Nothing. And for the first 99 pages, he admitted that negative gravitational energy is just a convention. Then on page 100, he does a transition. Some people would call it a bait and switch. He says, at infinite separation, there is no interaction. Therefore, this is the zero energy point. And thereafter in the book, from page 100 onwards, he assumes that the negative gravitational energy is an absolute fact, rather than just a convention. Why is Krauss's argument wrong? So you remember the original definition of energy. Energy is the ability to do work. All right? So according to the Big Bang model, the starting point is not infinite separation. The universe began with zero separation. So that's your starting point. And energy is required to push it apart. Does that make sense? Just as you launch the rocket, you start with low separation, push it up in the sky, that requires positive energy. And so the picture over here is a cosmological model of the Big Bang, starting 13.8 billion years ago with zero separation, and then expanding ever since. The Bible puts it another way. It says the Lord spreads out the heavens. In the year 2010, I was silly enough to attend the Global Atheist Convention in Melbourne. And Lawrence Krauss was one of the keynote speakers, and he talked on a universe from nothing. And what he displayed on his slide was gravitational energy equals minus G m1 m2 on R. So what's missing? The undefined constant. So he dropped out the constant. So hey presto, there you got it. Gravitational energy is negative. There were 4,000 atheists there, and they swallowed it without question. So 4,000 glassy-eyed atheists can't be wrong, can they?
If you were there, how do you know all the rest, and you didn't swallow it, how do you know all the rest swallowed it?
Sorry?
If you were there and you didn't swallow it, how do you know all the rest of them swallowed it?
Don't be difficult. I don't know. I don't know whether any of them thought that deeply about it. So what actually happened after his lecture, there was a queue of people. So he was selling the book, Universe from Nothing, and so you could queue up and get him to sign and have your photo with him. And I did that. I was the last one in the queue because I wanted to speak to him. And so I had a brief word to him. I said, I have a question for you. He says, well, sorry, I can't deal with it at the moment because I've got to run off and meet with my girlfriend. And but he says, I'll be around tomorrow. And so next day, I looked, never found him. So I missed out on actually being able to raise a question with him. Okay, we've been talking about Newton's equations all the time. General relativity supersedes Newton's equations. But Newton's equations closely approximate general relativity for things as we observe now. And general relativity mathematics is extremely demanding. But I've asked this question of many physicists and astronomers, and I've never met a physicist who could provide a qualitative explanation for why GE should be negative, let alone a quantitative one. Very early on the piece, after I read A Brief History of Time, Stephen Hawking pushed the same view, that general gravitational energy was negative, and never provided a reason why. So I went to, I just discussing this with a colleague at uni who was an astronomer, and I described how Stephen Hawking claimed that gravitational energy was negative, to which he responded, in that case, Stephen Hawking has lost his marbles. So here's my conclusion. Popular arguments on the web are based on Newton's equations. These appear to be false for the reasons I've given. Negative gravitational energy is a convention and is not a fact about reality. If the origin of the universe requires positive energy, where did this come from? And because the totally scientific explanation starts with energy can neither be created nor destroyed, but merely converted from one form into another. So if the energy of the universe is positive, there must be an energy injected at the beginning. So if this is the case, how does this affect the plausibility of multiverses? If you keep on creating universes and each one needs energy, where's that coming from? So at that point, I'll end my presentation And can you take charge?
We've got the universe magically creating itself out of nothing. It utilises the laws of physics as we understand them in order to do it. Where did those laws of physics come from?
So are the laws of physics just a property of the universe that we measure, or do they actually have an independent existence? And then where do they come from? So that certainly is a question which philosophers have debated without coming back with a definitive answer. But I think for a Christian, like one way would be to say it's from the mind of God, that God actually created the laws of physics. Because there's no explanation for the origin of the laws of physics. And they are quite marvellous. And just to see, just the fact that the system works is amazing. And it's something you wouldn't expect apart from a mind.
And they are independent of each other too, aren't they?
The laws of physics. Oh, there's lots of constants that are independent of each other, and one of them is a gravitational constant, which was some 8 times 10 to the minus 11 or something, and it's one of these fine-tuned parameters. But like all the laws of physics, like the conservation of energy and whatever, I don't know it's kind of a gaggle that works together. Isn't it?
All these people who postulate a multiverse postulate different laws of physics in each so-called universe. So if they have existence in their own right, then that cannot then be true. We have two mutually exclusive options. They may both be false, but they cannot possibly both be true.
The multiverse, I dare to speak. The multiverse theory comes out of string theory, M theory. String theory, the energy levels to observe it are so great that it's believed we'll never get there. We'll never be able to test it. And so you've got the existence of the multiverse dependent on a theory which is untestable, and the multiverse themselves are outside of our ability to measure, so you can never observe it, never test it. So you've got multiverse theory, untestable, dependent on a string theory, which is also untestable. So it's a lot of people debate, is this really science? But I guess it's harmless to speculate. And so they're trying to come up with theories that they can kind of validate by its internal consistency or the mathematics or whatever. And fine, go for it. But you're not on very strong ground. It's not empirical science.
For someone who doesn't understand much science, the multiverse or speculation doesn't solve the problem of the beginning of the universe. You still need a machine that generates multiverses, or you need something to start a causal effect. It doesn't solve the causal problem. It may infer the fine-tuning, right? But it still doesn't, as I understand it, solve what actually causes it, because they'd all have to have a beginning.
Yeah.
Yeah, but it goes somewhere as to trying to solve the fine-tuning problem of the universe, I suppose, yeah.
Did you want to include that?
Someone online got something they want to add in now? Blinded by science.
Yeah. Well, I mean, I suppose I could add a point. I'm not sure if it necessarily checks out with the math. I didn't follow all of it through with a fine tooth comb or anything like that. But um, speaking of the negative energy in terms of just the magnitude of negative energy, is the ability to do work from a negative energy. I mean, whether there's such thing as negative energy, I'm not sure, but can negative energy do work from going from, infinitely high or low negative energy to, not so negatively, not so high in magnitude in terms of the magnitude of that negative energy, if that makes sense.
I'm
So,
thinking that.
so rather than looking at the negative energy as just um sort of cancelling itself out, like the ability to do work obviously is the integral between two energy levels, and so you can still
Two
do work.
distances, yeah, energy levels, yeah, that's right, yeah.
So you can still do work going from one one gravitational energy state to another, even if it's in the negative
I'm not it now. You get
area
your drink.
of the um of the um you know Cartesian coordinates or whatever.
Yeah, well, what they're kind of postulating is energy is zero at infinite separation. So this kind of gives you, so if you kind of collapse it all, then you could draw energy out of that gravitational, somehow harness that gravitational energy to provide the other energy sources that are required, like heat and light and all this sort of thing.
Yes.
But it appears kind of by magic. All right, how does what causes you to grab hold of this magic pudding of gravitational energy to, like, where's it come from? And it just doesn't make sense. Because the universe didn't start that way. It's the argument is because with infinite separation, there's no interaction. Therefore, that's your 0 point. And so somehow that magic energy from infinite separation materialises and gives you the energy to create a universe.
What happens if they are quantum entangled before they got to infinite separation?
I've got no idea. Try and answer your own question.
Yeah.
I'm still having trouble with the whole concept of negative energy. Energy seems to me just existing, it either exists or it doesn't. The only thing I can get out of what you've been saying is that it depends on whether you're putting energy in or it's getting energy out.
Yeah, correct.
But that's got to do with what you're doing with the energy, not the energy itself. The energy itself is still something, a positive something.
Yeah, if you just get a ball, lift it up, the ball's gaining potential energy, isn't it?
Yes.
And then you let it go,
Yes.
and it falls, and that potential energy is being converted into kinetic energy until it hits something.
In other words, it's being converted from one form to another,
Yes,
not being created or destroyed.
correct. But the potential energy and as you've got a ball and you bounce it up and down, the potential and kinetic energy as independent items are going up and down.
But then there's also the elastic energy in the ball that enables it to do that.
Yeah. Well, it's just bouncing of it. That's a law of momentum. You're changing the momentum of it when it hits bounces.
Yep.
But you're not changing the kinetic energy at that point. I'm right.
To use a different example, if I've got a battery, I charge it, that's either positive or negative energy because I'm putting it in. And then when I discharge it to do something with that energy, it's coming out. So whichever it was in the first place, it's now the opposite now. If it was positive before, now it's negative. If it was negative before when I was putting in, it's now positive when it's coming out. That doesn't make sense to me. It's just energy that's going in or out.
Yeah, in that case, the value's going up and down, but it's not necessarily negative.
I think that's my point.
Yeah, that's a good point.
Someone else?
Did you have any thoughts, Steve? No? Any people in Zoom land got questions or comments?
Anyone want to question the mathematics?
Oh. You have to know what you're talking about to do that. I like to listen.
So, I wonder whether I should dare ask you whether I made it clear. I think, like, Josh wouldn't have had any problems with the mathematics, and I don't expect Steve would have neither.
You follow it?
I kind of realised how long it's been since I've done that sort of thing.
Yeah.
It's
You know.
another language.
Sorry?
It's another language. Yeah, mathematics.
Yeah, but a lot of it just kind of represents what you experience in daily life. You do actually understand it, because you've got the concept of driving a car. If you drive it faster, you're going to go further in a given time, and the longer you do, faster you go, further you go, and the longer you do it, travel, the further you go. That's integration.
And the quicker you stop, the more the energy that gets suddenly released.
That's right. And also, as you drive a car, you change your speed all the time. You get changing speed levels, speed magnitudes, and so it takes longer to get there when you have to slow down for a 40 speed limit.
But then you have the second law of thermodynamics, entropy, and we're always degrading. Ultimately, we'll just become one warm, fuzzy, floating mass of molecules, and that's it.
Yeah, so if physics follows their course, that's where you get the heat death.
That's right, yeah.
Like floating forever in a nice warm bath.
So did the argument make sense to you, Steve?
Oh, look, yes, I did. It goes back to my year 12, I think it was, physics. I had to remember some of those things a long time ago, but I take your point. There is a contradiction there that, well, you heard Krauss sort of just glossed over it, and glassy-eyed, what, 4,000 glassy-eyed atheists believe him.
For me, your point made sense, but I was struggling to try and come to terms with Krauss's point.
Well, what about infinite separation? There's no interaction.
Well, about negative energy and a universe from nothing, and none of that makes sense to me.
Well, he's saying that if you add everything together, they cancel out. So the sum total energy of the universe is zero.
Yeah, is he just making that one up, or does he have solid basis for that?
Well, it's basically the basic argument is that infinite separation is no interaction. But that's an irrelevancy, because the energy is work that you do to take you from one point to another.
And we do not have infinite separation. It's not a realisable concept.
Well, the starting point is zero separation. And so anything that deviates from that is positive. So you're increasing the potential energy of the universe as it expands, and that requires energy to be injected from another source. So it's not a free lunch.
It reminds me of the idea that out of the mouths of babes, because you ask even a baby or a child or a toddler if that box or ball can move on its own, and they'll say no, they have to push it. Yeah. So it's bleeding obvious. I'm with you. I can't, it doesn't make sense.
No.
Yeah. Even if it's at zero, you still need something to push it.
Yeah.
Yeah.
Or in other words, it's wishful thinking based on what you want to believe rather than following the facts where they lead, or the evidence where it leads.
Yeah. That's what it looks like. Now, a lot of these people are great minds who come up with this, and I'm just kind of looking at it from what seems obvious to me. So there is a possibility I'm wrong, all right, and they're right, and I just am not aware of their rationale. But what does it mean when we say that creation ex nihilo? So that's creation out of nothing, isn't it?
Yep.
All right. So if they're right, is that how God did it? And created everything from no energy? Or did God create the energy? And is this a demonstration of how God created the world from no energy? Do you see what I'm saying?
Yeah, but I think God goes back a step beyond that. That's still kind of starting with a conceptual universe that God then creates, rather than starting with no space, time, mass, energy, physical laws, totally outside, which is totally beyond our ability to comprehend because we are creatures of this universe. But if there is a God who did create this universe, an uncaused cause, so to speak, then he had to be external to all of those things.
Yes.
And so therefore none of those things are relevant in the sense of God creating them, but they are relevant, including all the physical laws as we know them, for those who want to have no God. They can't have the universe creating itself from nothing.
Yeah, I'm just wondering, like, if I'm wrong, is that a way in which God created the world from nothing? That the universe actually has no energy, zero energy?
Well, we can't rule that one out, but I don't see it as being at all required.
Yeah. Well, I've got nothing to lose, all right?
I
Yeah.
want to go to Gordon Stranger's, probably a year or so ago, he reminded us of the instance in Africa where milk was created. You may remember he told the story of a youth group that had been praying, I guess, about the spiritual side of things, the spiritual warfare, and a witch doctor was trying to poison them by putting milk in. It was going to poison them, and someone knew that was happening, but they didn't have any milk, and they always had to have milk with their tea. It was the tradition in that culture. And they prayed about it, and much as I think it was Elijah, was it, who told the widow to keep pouring oil, they just kept pouring milk. They knew they had very little milk, but they kept pouring and pouring and pouring, and something came out of nothing. And this was the spiritual side of things, but that was, if I may say, in a present day world. And then Gordon quoted a number of other instances of similar, creation of matter out of impossible situations. Something happened, and he gave a list, but particularly it was that case in Africa that was the one he really honed in, because he went there and he spoke to the people that had observed it.
So, does God often break the laws of physics? That instance seems like breaking the laws of physics, doesn't it?
Yes.
Or does God prefer to actually work through the laws of physics?
Well, look, I just mentioned it. It would go right back to the beginning. How did the first mass energy start from? Where did it come from? Well, at least we're talking about an instance fairly recent where something was created that just was not physically possible to be there at the moment, but they had that dilemma.
Yeah, like is the creation of the universe a miracle that goes beyond the laws of physics, or is it within the laws of physics? So, if my argument is correct tonight, then it's the creation of the universe is a miracle that defies the laws of physics.
Yep.
I disagree totally.
What?
Yep. I believe that the creation of the universe included the creation of the laws of physics, rather than defying the laws of physics, that the laws of physics were created with the universe.
Yeah.
So there's no defying in that.
But that's miraculous too, isn't it? The creation.
Miraculous. There are two words largely in the New Testament that are normally translated as miracle. One is sign, and the other one is basically a work of power. So, for example, we know that it is impossible to get a human being from the planet Earth onto the moon, and yet we know it has been done. It was done not through magic, but through the exercise of an enormous amount of power. A lot of energy was transformed from one type into another. There's also, so far as the laws of physics are concerned, we have come to understand more about that over the years as well. You're starting with Newton's laws, for example. That was a great revelation in his day. But then relativity, when that came along, has superseded Newton's laws and given us some other deeper understanding that we didn't have before. And then there is the quantum mechanics side of things, which we're still trying to get our heads around because it doesn't make sense to even the experts. But there's just so much more that we don't understand. And was it Kepler, Copernicus, one of them, said that our job as scientists is to think God's thoughts after him, to Kepler. The laws, what God has created in the universe is that they're put there for us to discover. And so that implies that there's still plenty more that we haven't yet discovered. So God can well do things using what he knows that we just don't know yet. So it's not breaking any laws of physics, it's just doing stuff that we don't understand.
So you're saying, all right, the free lunch hypothesis may be wrong, but maybe we'll find something else. Right.
We'll find God.
Yeah. All right. What's your problem? Oh, okay.
Yeah. It also comes back to something that I said in my last talk, that if God is God, then he's bigger than we can get our heads around.
Yeah.
And if he's not bigger than we can get our heads around, then he's too small to be God.
Yeah.
Anything more from anybody? Well, we might leave it there then, thank you. And